Hi, welcome to Discovering Design with Physics, Chapter 11, Review Questions. So we'll get right to it. Note that for these questions, we are given some of this information, which is the speed of light, c, and Planck's constant, h. And so we are able to refer back to those whenever we have problems that need those two values. And of course, those will be given on any exam as well. We're going to skip all of these definitions because we can easily get those from the book and start with question 2. Two waves have the same speed. The first has a longer wavelength, which has the higher frequency. And I'm not going to write out the whole answer, but just like many problems that we've had so far this year, we are just going to look at the formula. And so this is equation 11.1, the frequency of a wave. And F equals v velocity divided by the wavelength, okay? And so if the first one has a longer wavelength, that is going to make the frequency smaller, or lower, I should say. And so that is the answer. The second wave with the shorter wavelength will have the higher frequency. So the opposite of what I just said, right? So the first one will have a lower frequency because it has a longer wavelength, and the second one will have a higher frequency because it has a shorter wavelength. For question 3, which of the two basic types of waves is a sound wave, and what about a light wave? I'm not going to give you this answer because this is something that you should be able to find in the book, not quite as easily as some other things, but it's a pretty cut and dry answer. So I will give you a hint in case you haven't found it. The answer about sound wave is on page 285, and light waves are on page 299. For question 4, same thing. These are also very cut and dry answers for number 4, and they're also in pink highlighted portions of your book. So I would just search through those if you haven't found those in the section about sound waves. For question 5, a sound wave is traveling with a speed of 329 meters per second. What is the temperature of the air? So for this one, we're going to use equation 11.2, which relates to the velocity of sound. And with that equation, we have v sound equals 331.3 plus 0.606 times the temperature in Celsius. And all of this is expressed as meters per second because it's velocity. And I like to always solve for what we're trying to get, and so I like to rearrange it. And so rearranging this, we get the temperature equals the velocity of sound minus 331.3 meters per second divided by 0.606 meters per second. And so now we can plug all of that in. Our velocity of sound, of course, is 329 meters per second minus 331.3 meters per second, and then dividing all of that by 0.606 meters per second. So, of course, following rules for significant figures, we're going to do this part first and have that in correct significant figures. So 329 minus 331.3, we have to stay in the ones place because that's the least precise, and so we're going to get negative 2 meters per second divided by 0.606 meters per second. And so we'll get negative 3, and of course there's no units here because those canceled, but because we were solving for temperature, we know that that's going to be degrees Celsius. And so our final answer is the temperature is -3 degrees Celsius. For question 6, a sound wave is traveling through 27.8 degrees Celsius air. If its frequency is 540 hertz, what is its wavelength? So we have temperature is 27.8 degrees Celsius. We have a frequency equals 540 hertz, or 1 per second. And we need to know what the wavelength is. So to start with, we are going to need to use our velocity of sound equation, like we used up here, to get what our velocity is going to be. And then we can use the velocity and the frequency to determine the wavelength using equation 11.1. Okay, so I'm just going to go ahead and plug in the numbers into this velocity of sound equation that I've already written up in question 5. And so V sound equals 331.3 plus 0.606 times our temperature, 27.8. And all of this is going to end up in meters per second. So we get 331.3 plus 16.8. And those are to the same precision there. We've already rounded everything to get to 3 significant figures for this 27.8, or for either of them. And we get 348.1 meters per second. So there is our velocity. And so now we can use equation 11.1, frequency equals velocity divided by the wavelength. And so solving for wavelength, we would have the wavelength equals the velocity divided by frequency. Let's plug that in, 348.1 meters per second divided by 540 hertz, which equals 1 per second, right? And of course, our seconds are going to cancel. And when we do that math, this is to 2 significant figures. So remember that, because 540 would be 2 significant figures. And we will get 0.64 meters. So the wavelength is 0.64 meters. For question 7, at rest, a siren produces waves with a frequency of 915 hertz. If you're driving away from the stationary siren, this is a key here, at 17.5 meters per second, and it is 15.0 degrees outside, what frequency do you hear? If the car has the siren then starts driving towards you at 22.4 meters per second and you don't change your velocity, what frequency do you hear? So we have 2 separate questions here. So let's focus first on the first one. We are given the stationary frequency. I'm going to call this F station. And that is 915 hertz. Okay. We are given the velocity of the observer, and that's 17.5 meters per second, and it's driving away from the stationary siren. So I'm going to call this a negative 17.5 meters per second. And then we have the temperature. Okay. And so the first thing that we're going to do is determine what the velocity of the sound of the siren is. So using our velocity of sound equation, just plugging everything in, velocity of sound equals 331.3 plus 0.606 times 15.0 meters per second. So doing our multiplication first, we get 331.3 plus 9.09. And of course, our answer here will be rounded to the nearest tenths place because of our precision here and rules for significant figures. And so we'll get 340.4 meters per second. So this is our velocity of our sound. So then we can use equation 11.3 to determine the Doppler effect. Okay, so let's go ahead and write that out. So that is F observed equals velocity of sound plus or minus the velocity of the observer divided by velocity of sound plus or minus the velocity of the source. And all of that is times that stationary frequency. Okay. So let's plug that in here. I'm going to move this over just a little bit because I didn't leave myself enough room. Okay, so our velocity of sound here is 340.4 meters per second. And we're going to subtract the velocity of the observer, and that's why I put a negative here, because the observer is moving away from the siren. Okay, driving away from the stationary siren. So minus 17.5 meters per second. And then divided by the velocity of sound again. And for here, we add if the source is moving away from the observer, or subtract if it's moving toward the observer. Well, in this case, we are, the source is stationary. Okay, that's why I underlined that earlier. Okay, so that is going to be plus 0. And all of that times our stationary frequency, 915 1 per second. So let's put all of that together. We get 868 1 per second, or hertz. So the observed frequency is 868 hertz when the siren is stationary. Okay, so that is our answer for our first question. And then we're asked if the car that has the siren then starts driving towards you at 22.4 meters per second, and you don't change your velocity, what frequency do you hear? So in our Doppler equation, the only thing that's going to change then is now our V source is moving. Now it has a velocity and it is moving towards us. So let's plug all of that in. So F observed equals, in fact, we're not going to even rewrite out that top stuff. We're going to write what that equaled. So 322.9 meters per second. And now divided by the bottom part of this equation changes. So 340.4 meters per second. And when we're doing the bottom here, the plus or minus, we add if the source is moving away from the observer. So this siren is moving towards you, and so we're going to be subtracting. So minus, and then this velocity, 22.4 meters per second. And then, of course, we're multiplying all of that, again, times 915, 1 per second. Let's get what this bottom part is, and that's going to be 318.0 meters per second. And now we can divide and subtract this out, and we get 929 1 per second, or hertz. So for the second question, the observed frequency is 929 hertz when the siren is moving towards you. And that is question 7. For question 8, I'm not going to give you the answer for this one, but I will say look at those definitions that you should have already written out for sonic, ultrasonic, and infrasonic waves, and use that to help you with your answer. Keeping, biggest thing is that this pitch is too high for you to hear. For question 9, I'm also not going to straight up give you the answer for this one, but if you're having trouble, look in the pink highlighted section on page 296. Same thing for question 10, that highlighted section on page 296 should help you answer that. For question 11, I'd like you to refer once again to the book, and if you're having trouble finding this, it is part of a very long discussion on pages 298 through 299 that is exploring what exactly light waves oscillated through, because they didn't think it could be air. They thought it might be some kind of other gas, and then they eventually came to a conclusion. For question 12, that discussion on Thomas Young's double slit experiment is pages 297 to 298, and this is a pretty important discovery, and so that's why I'm really not going to give you much more information than that, but just read through that section on the double slit experiment, and you should quite easily be able to find out what was important, what were the final conclusions of his experiment. For question 13, we are still in this section about the wave nature of light. And starting on page 298, it starts talking about James Clerk Maxwell, and he was looking at electromagnetic waves. He actually wasn't looking at light, but he discovered something about the speed of electromagnetic waves that matched something about light, and so that is what we are looking for there. So look for that in your reading of this section where it's talking about James Clerk Maxwell's calculations. For number 14, we've moved on to a little bit different section starting on page 302, and it explains what Einstein published explaining the photoelectric effect, and he determined that there was something a little bit different about light, that it didn't just act as a wave, it had to act as something else, and that is what is really important about his explanation of the photoelectric effect. So look for that. For question 15, you see a bright yellow light and a dim indigo light. Compare their frequencies and amplitude. So I'm actually going to walk through this one with you. For light waves, higher amplitudes mean brighter lights. Okay, so we have a bright yellow light, and so that means that this yellow light is going to have a higher amplitude than this dim indigo light. Okay, so there's the amplitude portion of that. Then for the colors, the yellow and indigo, so if we look at Roy G. Biv, in that order, it goes from higher to a lower wavelength. Okay, now notice we're talking about frequency, not wavelength, but it relates, right? So the yellow, because it's earlier in Roy G. Biv, is going to have a larger wavelength than indigo. Okay, but remember that wavelength and frequency are inversely proportional. Okay, so when we talk about frequency, then the yellow light is going to have a lower frequency. So it has a higher wavelength than the indigo because it is earlier in the Roy G. Biv when we write that out. But it's going to have a lower frequency because frequency and wavelength are inversely proportional. Okay, question 16. You see a lightning bolt and 0.75 seconds later, you hear the thunder. If the temperature is 21.0 degrees outside, how far away did the lightning strike? So we have a time equals 0.75 seconds. We have temperature in Celsius, which is 21.0 degrees Celsius. Okay, so we can go back to using that velocity of sound equation and plug that in first to figure out what the velocity is. Then we can use the velocity and the time to determine the distance. So v sound equals 331.3 plus 0.606 times 21.0, and all of this will be in meters per second. So let's calculate out the addition portion of this formula, and we get 331.3 plus 12.7, and that gives us 344.0 meters per second. So there is our velocity. And so now we're going to use one of our old trusty equations where we had delta x equals v naught times t plus the acceleration times the time squared, right? And we have no acceleration, right? This is just a constant velocity. So we're not going to use that portion of it, but I did want to write out the whole equation. So our delta x equals our velocity, 344.0 meters per second, times our time, 0.75 seconds. Seconds will cancel, we'll be left with meters, and we get 258 meters, but we need to round that to two significant figures, so 260 meters. So it struck 260 meters away. For question 17, the frequency of a laser beam is 431 times 10 to the 14th hertz. What is the wavelength of the light it makes? And give your answer in nanometers. So that's going to be important. So let's write out what we have. We have frequency equals 4.31 times 10 to the 14th hertz. And we also have our velocity here because this is light, okay? And so from this first page, our given information, we were given c, which is the speed of light. So we're going to use that too, and so that's what I'm going to write in here for my velocity. So velocity equals 2.998 times 10 to the 8th meters per second. Okay, and so now using our frequency equals velocity divided by wavelength, we can determine what the wavelength is. Okay, so wavelength, of course, is going to equal velocity divided by frequency, and so 2.998 times 10 to the 8th meters per second divided by 4.31 times 10 to the 14th, 1 per second. So we're going to end up with meters, okay? We get 6.96 times 10 to the negative 7th meters. But like I told you, this is going to be important. We are not reporting our answer in meters. It's nanometers, okay? So we have one more step to get the final answer. So we're going to convert this to nanometers, and 1 nanometer equals 10 to the negative 9th meters. And so we will get 696 nanometers. The wavelength is 696 nanometers. Question 18. A metal has a work function of 5.1 electron volts. When light is shown on it, the maximum kinetic energy of the electrons released is 2.1 electron volts. What frequency of light was used? Okay, so we are given our work function, which has that symbol. Okay, we are given the maximum, call it electron kinetic energy. That's how I'm abbreviating that. E with the superscript negative stands for electron, and Ke is a kinetic energy. And that is 2.1 electron volts. Okay, so now we can use equation 11.5 to determine our answer. So we have maximum electron kinetic energy equals H, which is Planck's constant, times frequency minus our work function. And so H is also something that was given to us. That's Planck's constant on the first page of the review questions. So we can go ahead and write that down as something we know also. So H equals 4.14 times 10 to the negative 15th electron volts seconds. So let's go ahead and solve for F here. And when we do that, we're going to get F equals the max electron kinetic energy plus our work function divided by Planck's constant. So now we can plug everything in. We have 2.1 electron volts plus our work function, 5.1 electron volts divided by Planck's constant to the negative 15th electron volts times seconds. Okay, so electron volts are going to cancel all the way through, and we're going to be left with 1 per second, which is our frequency unit, so we are good there. So 2.1 plus 5.1 electron volts, we have 7.2. I'm not going to write any units because I've already canceled it. Divided by 4.14 times 10 to the negative 15 seconds. I could just leave it a second, not have a multiplication. Okay, and we get 1.7 times 10 to the 15th hertz. Okay, converting that 1 per second to hertz. So our final answer is the frequency was 1.7 times 10 to the 15th hertz. And that is all of the Chapter 11 review questions. Let me know if you have any questions.